Okay, so welcome to today's class. So for today, we are going to proceed on with the ML part. So for linear regression, and we are going to look at some additional models we can use, and that's the ridge and lasso regression, and maybe how different are they from. We are going to check how different they are from the other model, so the original linear regression. So I'm going to open yesterday's class code, and then we are going to use that as a continuation of today's class. So this is linear regression. So let me zoom in so that you can see what I'm typing and so that you can see all my code. Okay, so I've zoomed in. So once I've got my code here, what I'm going to do is I'm going to run all so that we can load our libraries and we can also load the tips dataset from yesterday's class. Then this is a plot showing you what I wanted to see yesterday. So here I created a line plot, but I guess a scatter plot can also work. So something like that, whereby you can see where the predictions mainly lie. So that will not be our focus for today, but our focus for today will be on reach and lasso regression. So before we do the practical part on ridge and lasso regression, we are going to check its theory part and see how different it is from the normal regression model. So what I'm going to do is I'm going to type in the equation for the normal linear regression model, and then we are going to include the equations for the two new models, the ridge and lasso regression models, and from there we'll get to see how the two different models work. So if I'm dealing with linear regression, then this will be my equation. So I will have something like y should be equal to mx. So it should be m1 x1 plus m2 x2 plus, then we go to plus mn xn plus c. So that's my normal linear regression equation. So when we go to, for example, ridge regression, so we have to introduce something else to that equation. So let's go to our notes and see what is that we introduce. So here we have ridge and lasso regression notes. So ridge regression is a regularization technique used to prevent overfitting in linear regression. So it adds a penalty term to the cost function, so which is the sum of squares of the coefficient of the features. The penalty term is controlled by a hyperparameter called the regularization strength, or alpha. Higher alpha value results in a higher penalty, which leads to a smaller coefficient value and a smaller model. So we won't check the code part, so we will head over to Google and I'll search for the ridge equation. So if we check the ridge equation, so if we go to the images part, you can see we have, maybe I can pick this equation here. So this is the normal equation, but for the ridge equation, we usually have this equation here. So we have our W, which is our weight, and our B, which is our term. So maybe I can visit this site and then we can extract this equation as a whole. So let me just use this image and then I'll explain. So I've opened the image in a new tab, and this is the equation that we have here. So if I was to transform this equation here, where we have y is equals to mx plus c, we will get something like y. So this will be negative y. Okay. So what we have on this side, plus m1 x1 plus m2 x2 and so on. So this is what we have at the moment. So, and what I can say is this part that is here, this is our fit train data well. So this is the equation that we use to get the predictions for y. But what we add again is something known as the penalty term, which is the alpha multiplied by the wi's, okay, wi's squared. So for example, in our linear regression equation, so for LR, we will take the LR equation, so what we have there, plus we get our alpha, then we take the sum of I is equals to 1, maybe up to n, then here we will have our mi squared. So this is the part that we add for our ridge regression model. Then for lasso regression, we usually take the absolute value. So it will be LR plus, let's get that from Google again. So you can see we are taking the absolute value for WI. So we will have our alpha, then we take the sum of all values where I should be equal to 1 up to n. Then we have our mi, so the absolute value for mi. So that's the equation that we have here. So this is the difference between ridge and lasso regression and the normal linear regression model. So I won't go deep into these equations. So what you needed to know is this additional part, which is the penalty part. This is the penalty term. So what it does is this part allows us to ensure the model does not overfit. So it means that it will limit the kind of accuracy you are going to get for your model, so that you won't get a model that is 100% accurate, okay, while it should be 70% accurate because it's maybe overfitting. So that's the job of these two models. So you can use any of them when fitting your models. So the only thing that we usually do different here is, so when we are creating our models, so for example, the lasso regression model, so here we will go to the practical part. So here we'll have from sklearn.linear model import lasso. Then I can add a comma and also say import ridge. So for this part where we are instantiating our linear regression model, you saw that we never specified the alpha. But here for ridge and lasso regression model, when we are instantiating the model, we have to specify the alpha. So here what I'll say is I will instantiate the ridge regression model. So we'll have ridge small r being equal to ridge. Then here I will have my alpha value. So again, what you need to know is when you are dealing with the ridge regression model, so your alpha value ranges from 0 to 1, okay? So you need to choose a value in between 0 and 1. So how do you pick the optimum value for alpha? So we will discuss that in another class. So once we've instantiated the ridge regression model, what we do next is we feed the model to our data. So we will have ridge dot feed, then we feed these to our x and y. And then the last thing we can do is we can get the score, because here we don't really need the predictions as of yet. So I will get the model score, and here we will have ridge.score xy. Then I can run that. So our ridge regression model has an accuracy score of 0.46. Then Lasso, not Lasso, but linear regression has the same accuracy. So let's compare between the two and see which one has the highest accuracy. Yeah, so our linear regression model has a more higher accuracy as compared to the second model. But that's because we are using a different model with a different equation. But if you focus on the first two digits that we have here, then you'll see that the accuracy is almost same. Then what we do again is we can fit our lasso regression model. So we will have our lasso regression model here being equal to, so we can have lasso small l being equal to lasso, then our alpha, we specify it to be equal to 0.05. Then we feed the model, and then we get the model score. So if we do that, we get a slightly lower accuracy score. So I'll give you guys 5 minutes to copy this, and then we can proceed on with the discussion. So from here, so this is a continuation of yesterday's class notebook. So copy what we have up there and what we have down here, and then we can proceed. Okay, so hope you are done with this part and we can proceed on to the next part. So I'm going to print out the scores of the different models. So rounded off to two decimal places. So for example, we can have print lasso dot score. So I can type in here F, just a minute. So I'll round these off to the nearest two decimal places. So this will be the Lasso regression score. And then we can print out also the ridge regression score. And lastly, we can print out the linear regression model score, rounded off to two decimal places. Okay, so we have an error. I'll have to fix that. It's the number of brackets I'm using, so let me correct that, and then we can get the correct output here. Okay, just a minute. Okay. I now know where the error is. So I have to include my X and Y. I forgot that. Let me run this and see where we'll get the error here. So I excluded my X and Y, and that's why we got this error. So if we run this, you can see that these three models have the same score, but the difference that comes in is on the decimal points that we have here. And as we've discussed, that is because of this additional part that we've included here for regularization. So if the scores for Ridge, Lasso, and linear regressions had some significant differences, then we will say that our linear regression model was overfitting. And we will prefer to use these other two models instead of using the linear regression model, which has the straightforward equation. Okay. So the next thing we are going to look at is maybe one of the advantages that we have for using the Lasso regression model, and that is feature selection. So knowing which features are important in making predictions to our target variable. So if we go to our notes, you can see this part here. Okay, so lasso regression can be used for feature selection by setting a high regularization strength, so that is the alpha value, that results in a high penalty for large coefficient values. So if a value has a large W term or has a large weight, which is this M part here, then we will say that that feature is not that much significant, and the lasso regression model will penalize that feature more. So this causes some of the coefficients to become exactly equal to 0. So it means that these coefficients will be reduced to 0, some of them. And we will know that those features are not that much important, which means that the corresponding features are not important for the model. So I'm going to copy this part here, the last part. And using this last part, we are going to get the feature importance of our model here using the tips dataset. So if I run this, you can see that these are our features, and we have the features ranked from from the best to the worst feature. So that's basically what we have here. So important features. So for the important features, we have feature number 0. So feature number 0 is important. Feature number 1. Feature number 1 is important. Then we have feature number 3. So we've skipped feature number 2. And after skipping feature number 2, we've skipped feature number 4. So we have feature 0, 1, 3, and 5 being important. And if we type in tips.columns, we can get to know the columns that are important for us. So we have the total bill column, we have the tip column. So it should actually be X and not tips. So if we check this, you can see the total bill, sex, day, and size. Those are the most important columns in predicting tip amount. And if we check all the columns that are there in the data set, you can see that being a smoker doesn't contribute much to the amount of tip you will leave, and the time of the day. So whether it is during dinner time or lunchtime doesn't contribute much to the amount of tip you will leave. So that's one of the most important things you need to note concerning lasso regression. So using the coefficients, you can be able to extract features that are important. So these are the codes that you use for that. So I'll give you 5 minutes to copy that, and then we can wind up today's class. And you can ask questions if you have any. So actually what I'll do here is, so as you are copying this code, what I'll do is for this data that we have here, I'll pick these columns and then we are going to fit another model. Yes, anyone with a question? Okay, just a minute, I'll scroll to that. So before you maybe copy this, let me go ahead and fit another model, a second model, whereby we are using only these important features that are here, and we get to see what differences it will make. So we are going to have lasso dot fit, and then we are going to have x, and for x I'll select the columns that are important, and then we are going to have our y here. And then lastly, we are going to have lasso dot score. And then we score again on these same columns. So let's run that and see if everything is okay. So we get 0.4629, while up here we had 0.4629. So you can see after eliminating these two columns, the sex and the time column, we get roughly the same score because these columns had no impact on our predictions. So it reduces the amount of data we'll have to use for fitting our model, and also the amount of computation we'll have to do. Yeah, so that's one of the important factors you have to consider. So let me scroll up. So we are here. You can copy these codes and then we can proceed. So first start with this. I'll give you 5 minutes to copy these, and these, and then another 2 minutes to complete the other code. So I'll now scroll down to these lower code cells so that you can see the other code parts. I'll delete this because it's not that much important, and then you can copy the other code parts. Okay, so you should be done by now. So if not done, you can inform me, and then I can give you a chance to complete what we've done. So I'm going to summarize what we've looked at for today, and then we can call it a day. So first of all, we have two new models here that we can use for fitting multiple regression models. So the first one is the ridge regression model. And for the ridge regression model, we add this part to the code. So we add an alpha multiplied by the summation of all the weights squared. Then we have the lasso regression model where we have the normal prediction equation. Then we add the alpha multiplied by the absolute value of each and every weight term. So the summation of all those values. And if we run these two models, so after specifying our alpha, we get similar scores as to what we had in our linear regression model. So you can see the scores are simply the same. But we also again checked and saw that for lasso regression, we can eliminate features that are not that much important or features that don't make a significant impact when it comes to predicting our target variable. So for example, if we checked here, we saw that the smoker column and the time of day column did not make any significant impact in trying to predict the tip value. And once we eliminated those two columns, we saw that our predictions values still remain the same, confirming that those two columns were not that much important. So yeah, that's basically the advantage of using lasso regression. And the advantage of using lasso and ridge regression is we avoid overfitting. So we will discuss overfitting in another class, and we will get into detail and see how do we avoid overfitting in such cases. So that's it for today. If you have questions, you can ask. So I'll go ahead and upload this video